So guys, now let us try to understand that CPU generates only virtual addresses while executing your program. So variables in the programs are just symbolic names of addresses, right? So you must have written a program, and in that particular program you must have defined certain variables like variable int a, int b, int c, and many others. So those variables in the programs are just symbolic names of addresses. Variables are there for our convenience so that we can read and write computer instructions in human readable format, right? Can you imagine the situation that instead of using variable names, we had to use direct memory locations or addresses in order to save our value? How horrible our program would have been look like. In fact, you would not be able to recognize a very short program only after few minutes you have written, right? So variables are there for our convenience. At the lowest level, programs are translated into machine code which only deals with virtual addresses. The machine code do not deal with variable names, right? Machine code is not aware of variable name like int a, int b, or int c, or any other variable name. Variable names are replaced by their actual virtual address locations in the machine code. So your program translates into machine code after compilation. In machine code, variables are replaced by their actual virtual addresses. Machine code then executes and performs read and write operations using addresses of variables instead of variable names, right? So just to take an example, suppose in your program you have a variable a, and inside that variable you are storing value 10, right? So this instruction after compilation would look something like this. Now this piece of instruction is actually a code of assembly language. I cannot write machine code directly because machine code is all binary. So assembly code is actually that piece of code which is closest to the machine code. And therefore I have written here the assembly code which is equivalent to this line of instruction of your high level program. So you can see that this piece of code actually talks about only in terms of addresses. There is no variable name a used in this instruction. Now EBP is a base pointer register, and you will understand this instruction only if you had gone through the stack memory section of this course thoroughly. We will going to do a little recap in the next slide. So machine code is not aware of any variable name like int a, int b, etc., which you have used everywhere in your high level program. We have already learned that all local variables and argument of a function are accessed by CPU by adding or subtracting to base pointer register of the current stack frame, right? Now I want you to recall the usage of base pointer register when we were discussing the stack memory management in the previous section of this course. So let us do a little recap in the next slide and try to understand that when CPU executes your program, it references every variable of your program using virtual addresses instead of using symbolic names. So guys, now let us do a little recap. This slide must be familiar to you. We discussed this slide when we were discussing stack memory management, right? So in this slide, you have a program on the left hand side, and this program is actually executing in its function a, right? So because the function a is currently in execution, therefore stack memory contains the stack frame corresponding to the function a on the top of stack. So you can see that this is the stack frame of the function a. Now I expect you that you already knows that how this stack frame was built. So the point that I'm trying to emphasize in this slide is this point. That is, base pointer register value is used by the processor to reference arguments and local variables of the current stack in execution, right? So you can see that as per this diagram, the value of base pointer register is the following address. Now for simplicity, let us assume that this represents 100, right? So if the processor wants to access the variable d, now d is a local variable of the function a, right? So if the processor wants to access and perform read or write operation on the variable d, the processor will generate an address 96, right? The addresses are generated in relative to the base pointer register value. Now the base pointer register value, for example, contains 100. So 100 minus 4 means 96. So 96 in this example will be the virtual address of the variable d. Similarly, if the processor wants to access variable c, it will generate an address 92, right? Similarly, to access the variable a, the processor will generate a virtual address 108, and to access the variable b, the processor will generate a virtual address 112. So the point I'm trying to make here is that whenever a processor executes your program, and during the course of execution of the program, if the CPU or processor wants to perform read or write operation on your variables, processor issues or generates virtual address of those variables. Processor is not aware of the symbolic names, that is D, C, A or B, right? So going forward, CPU generates millions of virtual addresses during the course of execution of a process. These generated virtual addresses are then mapped to corresponding physical address by MMU using concept called paging, right? So we are about to dive deep into the concept of paging. We are in the process of building basics. CPU then issue the instruction to either read or write the data on the mapped physical addresses. Now let us understand the entire picture in totality on the next slide.